Hello, everyone. My name is Kinan, and today I'll be presenting to you our work on K9db, privacy-compliant storage for web applications by construction. This is joint work with all these wonderful people from the Ethos group at Brown University. So in recent years, we've seen a surge of privacy laws, including the EU's GDPR, the CCPA in California, among many others. And in response to this, application developers must now ensure that their applications comply with these laws in order to avoid heavy fines. A common and challenging requirement to comply with, is common in all of these laws, is that applications must allow the users to access or delete their data. This is the main focus of this work. In addition, these laws mandate that applications take reasonable steps to secure their data, and this is often interpreted to require encryption at rest. Our work also satisfies this. These laws include a variety of other stipulations around consent, cookie banners, purpose of processing. These are simpler to comply with from a technical perspective and are out of scope for this work. To demonstrate to you that compliance is indeed challenging, let's look at the following scenario. Say that we have Alice, the user of some applications, and some application. Let's say that Alice requests deletion of her data. Let's wear our developer hat and try to design a mechanism that satisfies this request. The first thing that the developer needs to do is to identify Alice's data in the database. In a real-world application where the schema is complicated and you have many tables and many relationships, this is actually pretty challenging. Furthermore, some of Alice's data may be shared with other users, and the developers need to determine how to handle such shared data. This is application-specific, and it depends on the sensitivity of the data in question. So for example, maybe it's OK to keep chat messages that Alice exchanged with her friends, but not sensitive medical records that she shared with doctors. Developers also often need to retain some of Alice's data, perhaps in anonymized form, for other legitimate purposes that are allowed for by the law. For example, maybe the developer needs to retain some anonymized financial transactions in order to comply with tax laws. And finally, the developer needs to update caches and backups that may contain some of Alice's data. Now, naturally, at this point, this is all too much, and the developer is freaking out. But unfortunately, the traditional SQL databases that we have do not really help here. They offer no support for compliance, and they shift the burden of compliance entirely onto the developers. In this work, we present K9db, a compliant by construction database that provides support for access and deletion requests, as well as other compliance invariants as built-in primitives. This results in a happy developer and better data privacy and control for end users. Now, in this work, our main goal is to help developers get compliance right. We want to do this while requiring low developer effort and few application changes, while at the same time having performance comparable to traditional SQL databases, which offer no built-in support for compliance. And in this work, we assume that the applications and their developers are honest, but fallible. We want to reduce the burden of compliance. We also want to avoid costly bugs. And we think that this is reasonable because the penalties imposed by the law are sufficient to deter malicious behavior in many cases. All right. In this work, we encountered three main challenges, and these were outlined the rest of this talk. The first challenge is that K9db must capture application-specific compliance policies, especially around shared data and anonymization. The second is that K9db must correctly enforce these policies when handling access and deletion requests, and must make sure that any invariants required for compliance always hold. And finally, it must do so while maintaining good performance. To address the first challenge, we designed a set of high-level schema annotations that developers use to express their policies to K9db. Internally, K9db represents this policy as a data ownership graph, or DOG for short. So let's look at this in more detail. Here's a look at a common application scenario where users whose information is stored in the users table exchange messages among each other, which are stored in the messages table. And note that each message has two foreign keys, one to its sender and one to its receiver. The first thing to note is that rows in this users table correspond to human end users, i.e. data subjects. And those data subjects have rights to their data under privacy laws. So for example, Alice should be able to request access or deletion of her data. Developers express this to K9db by annotating the users table with the data subject annotation. Now let's look at what happens when Alice requests deletion. Let's say that we have two messages related to Alice in our database. One she sent to Bob, and the other she sent to Carol. And let's say there's a third message in there that is not related to Alice. The application developer is now faced with a policy decision. Specifically, what should happen to these messages that Alice exchanged with other users? An example of a reasonable policy here is joint ownership, which is indeed what Facebook and many other applications do for these direct messages in practice. According to this policy, a message should only be deleted when both its sender and its receiver request deletion. The application developer expresses this policy decision to K9db by annotating both foreign keys with the owned by annotation. Given these annotations, when Alice requests deletion, K9db does not delete any messages just yet. But if in the future Bob also requested deletion, then K9db deletes the first message that Alice sent to Bob, but retains the other two messages because they're related to at least one other active user, which is in this case Carol. Now, K9db provides other annotations that you can read more about in the paper. And using these annotations, by combining them in different ways, the developers can express alternative policies. For example, a policy that dictates that a message should be deleted when either the sender or the receiver requests deletion, or when only the sender requests deletion. You can think of other policies as well. In real applications, these policies can get a little complex. And so K9db provides an explain compliance command to help developers reason about their policies and make sure that they have their annotations just right. Internally, K9db represents these policies and these annotations using the data ownership graph, or DOG for short. The DOG is a multi-graph where every node represents a table, and every DOG needs to have at least one data subject table, which is highlighted using double circles. The edges in the DOG correspond to annotated foreign keys that carry some ownership semantics. And the edges always point towards the data subject, either directly or transitively, even if the underlying foreign keys point in the opposite direction. Here's an example of a slightly more complicated DOG that corresponds to a social media application. And this DOG highlights a couple of important patterns. The first one is shared data, which has more than one owner. And we also see a chain of edges here that represents transitive ownership. So the rows in the tagging table refer indirectly to their owner via the corresponding story. This DOG acts as the ground truth that specifies which data K9db must delete or return in response to a deletion or an access request. And it can do this because of two properties. First, if we starting at some row, let's say in the tagging table, K9db can identify all the owners of this row by traversing the outgoing edges in the DOG transitively until it reaches the data subject table. Conversely, starting at a data subject row, K9db identifies all the data that is owned by that data subject by traversing all the edges in the opposite direction. OK, so we just saw how K9db captures application-specific compliance policies and represents them using the DOG. Let's now look at how K9db enforces this policy to correctly achieve compliance. K9db does so by relying on an ownership-aware storage layer. And this storage layer is configured by the DOG and has built-in support for deletion and access requests. So K9db stores data organized by its owners. What that means is that the storage layer in K9db consists of a collection of per-user microdatabases. Each microdatabase stores exactly the rows that are owned by the corresponding user. K9db can do this because of the DOG. So for example, when a row is inserted into K9db, K9db uses the DOG to identify the owners of the row, and then inserts the row into the correct microdatabases. K9db also uses this DOG in order to handle updates and deletes, and this allows it to ensure that the contents of every microdatabase is always consistent with the DOG at all times. An important consequence of this design is that K9db stores copies of jointly owned records in all of the microdatabases of their owners. And this may seem unorthodox because we're storing copies, but this has 3 advantages that are critical for compliance. The first advantage is that this simplifies handling of access and deletion requests. So for example, if Alice says, delete my data, it's sufficient to delete her microdatabase, regardless of whether some of her data are shared with other owners or not. The second advantage is that this allows K9db to use different encryption keys per user. And this guarantees compliance in the presence of backups. When Alice requests deletion of her data, K9db also deletes the key, and that in turn makes sure that her backups are in effect deleted, because the key that decrypts them is lost. One challenge is that regular application operations that are not related to compliance may still end up violating compliance, for example, by disassociating data from its owners. Using this microdatabase's design, K9db detects and rejects violating operations. For example, orphan data cannot be stored in any user microdatabase, and so it's easy to detect. With that said, a common pattern in web applications is to temporarily create orphan data and then either delete it or reintroduce owners to it. And K9db provides compliance transactions in order to safely support such sequences. A compliance transaction can temporarily have orphan data, but K9db only commits it if it restores compliance by the end. All right, so let me highlight a couple of optimizations in the interest of time. First, K9db realizes our microdatabase's design over a single RocksDB data store. This allows us to use secondary indexes as well as RocksDB iterators, snapshots, and transactions to efficiently handle queries. Second, K9db serves complex queries from an integrated in-memory cache. This cache is based on materialized view, and K9db updates it in response to every write, including deletion requests. So the cache is always up to date, and it's always compliant. We evaluated K9db based on several real-world applications. And in our evaluation, we looked at 3 important questions. First, what is the impact of using K9db on the end-to-end application performance? Second, how effective are our optimizations? And third, how much developer effort is required to use K9db? For the first question, we evaluated this based on 2 applications, Lobsters, which is a link aggregation and discussion board, and OnCloud, which is a file sharing application. I'll only show you the results for Lobsters in the interest of time. In this experiment, we generated a load that is based on the actual deployed Lobsters. This load corresponds to 9 application endpoints, such as opening the front page or reading a story. The x-axis shows the endpoint, and the endpoints on the left are read-heavy and more common, while the ones on the right are write-heavy and rare. The y-axis shows you the median latency in millisecond, and so lower is better. As a baseline, we chose MariaDB, which is a popular fork of MySQL, because it supports RocksDB as a storage engine just like us. Remember that MariaDB and these other SQL databases do not offer any compliance features built in. And here you can see the results for K9db. And the key takeaway is that K9db achieves compliance with performance that is comparable to the baseline. Looking deeper, we can see that for the read-heavy endpoints, K9db matches or outperforms the performance of MariaDB because of the use of in-memory caching. While K9db has competitive performance for the write-heavy endpoints. Now, this was the median latency. Let's look at the 95th percentile tail latency. And here, the picture looks a bit different. We see that in the tail, K9db has more overhead on writes and in this comments endpoint. And to understand why this is the case, we ran the same experiment with an identical version of K9db with encryption disabled. And we noticed that encryption is a significant portion of the overhead on writes and in this comments endpoint, in the tail. For example, the tail of the comments endpoint corresponds to stories that have thousands of comments. And so K9db needs to perform thousands of decryptions when retrieving them. If they choose to, developers can accelerate this endpoint by using K9db's integrated cache, which is in memory and unencrypted. Our paper addresses the other evaluation questions. We show that our performance is comparable to a baseline that uses caching and has reasonable memory overhead. Our paper also shows that K9db's storage layout optimizations are critical for good performance. And finally, we show that K9db can capture real compliance policies of 10 web applications that range from social media to e-commerce and conference submission systems. In conclusion, K9db is a database that provides built-in support for compliance with GDPR and other privacy laws. K9db relies on the DOG, the data ownership graph, which is its key abstraction that captures the compliance policies of real web applications. And it also relies on its ownership-aware storage layer, which organizes data into per-user microdatabases. K9db achieves compliance while also exhibiting performance that is comparable to SQL databases, which have no built-in support for any compliance features. Our code is available on GitHub. Thank you.